In March 1918, a massive United States Navy vessel sailed north from the Caribbean, charting a direct course for the East Coast. Somewhere off the Virginia Capes, it completely disappeared. The scale of the loss was unprecedented at the time. 306 men and 10,800 tons of cargo were erased without a single piece of debris, an empty lifeboat, or a distress signal. In the absence of physical evidence, speculation filled the void. Bizarre diplomatic cables reporting a mutinous crew and a volatile commander fueled a growing paranoia, eventually helping cement the ship as a cornerstone of the Bermuda Triangle myth. But naval architecture is governed by physics. Steel does not evaporate. The total absence of a distress call provides a specific forensic profile. It suggests an event that happened with such speed that it overrode every maritime protocol and survival mechanism on board. To understand how a ship dies, you have to understand how it was built. The USS Cyclops was a Proteus-class fleet collier. Its most distinct feature was the massive steel superstructure running the length of its main deck. The Navy designed these ships to carry loose bulk coal across the ocean to refuel active warships. Total destruction of a 542-foot steel Leviathan required a specific sequential alignment of metallurgical decay, cargo kinetics, and environmental force. To see how those forces aligned, we have to look past the ocean entirely and examine the invisible decay inside the ship's skeleton. This 3D cross-section shows the lower hull of a Proteus-class collier. It relied on continuous longitudinal steel I-beams to act as its rigid spine. But when bulk coal gets damp, it generates acidic runoff. Over years of service, that acidic water pooled in the bilges, silently eating away at the lower flanges of those vital I-beams. This was a systemic, class-wide design flaw. The proof of this decay was documented years later during a 1932 dry dock inspection of the Cyclops' sister ship, the USS Jason. Inspectors found that over 50 feet of the Jason's longitudinal I-beams had completely rusted away. In that section, only the thin outer hull plating was holding the entire ship together. By March 1918, the Cyclops had been operating in the exact same conditions, carrying the exact same acidic cargo, without undergoing a structural overhaul. When the Cyclops left port for the final time, its internal safety margins were already severely compromised. The hull was brittle, waiting for a trigger. That trigger began in Brazil, with a very different payload. Instead of coal, the Cyclops was ordered to transport raw manganese ore for munitions manufacturing. Manganese ore is vastly denser than coal. To reach the 10,800-ton limit, the crew only needed to fill a fraction of the hold volume. This left massive, empty headspace above the dense ore. Because the hatches used basic canvas tarpaulins, heavy seas easily penetrated, pouring water directly into that empty space. As the seawater saturated the dry ore, the constant mechanical vibration of the ship's engines churned the mixture, turning the solid rock into a thick, heavy slurry. In marine engineering, this phase change is known as liquefaction. Liquefaction introduces a highly lethal dynamic to any vessel, the free surface effect. When a ship rolls, liquefied cargo does not stay in place. The mass flows freely toward the lowest point, violently dragging the vessel's center of gravity off-center. Once shifted, the ship cannot right itself. The fluid's kinetic energy locks the hull into a permanent, severe list. The Cyclops was no longer a stable transport. It was a top-heavy pendulum carrying a massive shifting liquid wrecking ball inside its hull. The final catalyst arrived on March 10th. A violent gale swept over the Virginia Capes, hammering the region with massive seas and 40-knot winds. The Cyclops sailed directly into this storm with a critical mechanical handicap. A cracked cylinder in her starboard engine forced the crew to operate on a single off-center propeller shaft. Running on one shaft at low speeds strips a ship of its steerage way. The rudder simply lacks the water flow required to turn the massive hull against the wind. Unable to keep her bow pointed into incoming waves, the Cyclops was pushed sideways. She fell beam to sea, taking the full broadside impact of the wave troughs. This animated profile demonstrates the extreme mechanical stress she was subjected to, hogging and sagging. The wave peaks lift the bow and stern, leaving the heavy midsection totally unsupported. Then the trough drops the ends, concentrating the entire weight directly onto its center. The trap was set. A violently shifting liquid payload inside a deeply corroded skeleton, bending back and forth across the troughs of massive waves. The weakened steel I-beams finally reached their yield point. The metal tore, and the ship's spine snapped. Splitting cleanly in half instantly destroyed the hull's watertight integrity and any remaining buoyancy. With the center of gravity already dragged off balance by the liquefied manganese, the heavy steel superstructure acted as an anchor, violently rolling both halves upside down. A catastrophic structural snap happens instantly, causing the ship to plunge into the abyss in a matter of seconds. There was no SOS and no lifeboats were launched because the structural snap and capsize afforded the crew zero reaction time. The Cyclops was the first failure of a flawed blueprint. During the Second World War, two of her identical sister ships, the USS Proteus and the USS Nereus, also vanished without a trace in the Atlantic. The pattern is precise. All three were aging Proteus-class colliers. All three carried high-density metal ore into severe storms and vanished instantly. This reproducible data points directly to a systemic architectural vulnerability, dismantling any remaining myths. The men of the USS Cyclops were not victims of the Bermuda Triangle. They were caught in the cold, unforgiving math of structural engineering.